Hello boys and girls, welcome. So let's do a little review. A couple lectures ago we learned a very important secret. Actually we learned a couple secrets. We learned the secret of life. Stay thirsty, my friends. But we also learned the secret to solving triangles. That secret was, if you recall, that the secret relies on one very important idea: knowing one of the ratios. One ratio is all it took. If you know one ratio, then so long as you knew one of the sides, it would be all over. One ratio on one side and you could solve everything about the triangle. You guys remember that? Remember, that is such a crucial idea. I think that even calling it the secret might not be good enough for the stature of that idea. I think really it should be called more like the fundamental theorem of trigonometry. Not a lot of people call it that, but I've just been thinking lately that we should call it that. Why not? All right. So, anyways, that was such an important idea. Let me review for you. Suppose you knew this ratio. Let's go right on this guy. If you knew this ratio was, say, 25%, okay, and you knew this side to be, I don't know, 6. That's all it took. One ratio, one side, game over. Because then you could just use your noodles here and think, all right, to go this way you multiply by 25%. To go back you would divide. So you take 6, divide by 25%. That would give you 24. Then you got two of the sides. Pythagoras would deliver the third, and game over. I told you. Crucial idea. The secret. Really, it should be called, I think I'm changing the name officially from the secret to the fundamental theorem of trigonometry. Isn't it cool to be me? I just make up theorems as I go. Why not? It's audacity, buddy. Pure audacity. No one has done it before. It's about time. This is so fundamental. One ratio, and one of the sides, game over. That is crucial. Okay, that was nice. After we did that, we went on to learn a couple ratios, actually. Or we learned the ratios in some very special cases. So let's real quickly the ratios we know. This one right here, the 30-60, piece of cake. We've dominated that one. We know that if this is 30 degrees, across from it we find the small side. Across from 90 we always find the hypotenuse. Across from 60 we always find the medium side. And we know exactly what the ratios are. This ratio is always 50%. To multiply, take the hypotenuse, multiply it by 50%, that gives you the small one. This ratio is always multiplied by the square root of 3. You take the small one, multiply by the square root of 3, and you get the medium one. And knowing the ratios, what is that? That's the fundamental theorem of trigonometry. The idea that knowing the ratios gets you everything. As long as you have one side, you're good to go. Not even all the ratios. All you need is one ratio. Ratios are so powerful. Fundamental theorem of trigonometry. And this was good. We need the ratios here at the 30-60 theorem. And so I have to whisper because my daughter's asleep. And we also knew the 45-45 ratios, meaning that if this was a 45-degree angle, this was 45-degree angle, we knew exactly what the ratio was. To go this way, you would multiply by the square root of 2. Or said differently, to go backwards, you would divide. And of course, this is the same. These ones are equal. You could multiply by 1 if you want, but they're equal. Those are the ones we knew. Of course, we also knew this one, the almost triangles. These ones are almost the same. You just multiply by 1. If this was 10, this would be nearly 10, or vice versa. This would be nearly 0. On these ones, we knew exactly what the ratios were as well. So let's put the ideas together. The fundamental theorem of trigonometry. If you know one ratio and one side, you're golden. In some special cases, we got lucky. When the triangle is 30-60 triangle, we got lucky, we know the ratios. Check. 45-45, we know the ratios. Check. Almost triangles, we know the ratios. Check. But then comes the next question. We know the ratios for 30-60, 45-45, and almost triangles. Which ratios would you like to know? Which other ones? If your triangle was, say, 20 degrees here, wouldn't you like to know the ratios? Yes. What if it was shaped differently? What if it was, I don't know, 5 degrees? Would you like to know the ratios? Yes. What if it was more than 45 degrees? What if this was 70 degrees? Would you like to know the ratios? Yeah, no matter what the shape of the triangle is, we'd like to know every single one of these ratios. We'd like to know all the ratios of all the possible triangles. Why? Because of the fundamental theorem of trigonometry. If you know the ratios on one side, game over, you're the winner. You'll be the life of the party. You got it? Putting all the ideas together? These are ideas that have to fit in nicely together. First idea, knowing the ratios, that's the secret. That's the fundamental theorem of trigonometry. Second idea, although we know some ratios, we got lucky. Really, the ratios that we would like to know is, guess, all the ratios, all of them. For every possible triangle, we would like to know the ratios. Got it? So, that puts us to today's lecture. I picked some random little triangle and I asked the question, how would you find the ratios? Suppose you were just a very curious person and you had no clue how to find the ratios. You're not lucky, it's not a 30-60 or 45-45, it's not one of the famous ones. What would be the layman approach to ratios? Just a simple-minded approach, a very primitive one. Here's an idea. We could take a protractor and just try to measure the degrees so we know what we're talking about. So we would measure, you say, oh, that's about, what is that about? Is that about right? That's about 17 degrees. So this particular triangle measures about 17 degrees. So we'll put it right there. We'll mark it. This is 17 degrees. And we're asking on a 17 degrees ratio, on a 17 degrees triangle, right triangle, what is this ratio? What is the ratio of the opposite one, the side opposite of 17 degrees and the hypotenuse? What would this ratio be? If you're a layman, if you were just a kid learning this, just a curious child, how would you figure out that ratio? Well, I got an idea. I picked some random little triangle and I asked the question, how would you find the ratios? Suppose you were just a very curious person and you had no clue how to find the ratios. You're not lucky, it's not a 30-60 or 45-45, it's not one of the famous ones. What would be the layman approach to ratios? Just a simple-minded approach, a very primitive one. Here's an idea. We could take a protractor and just try to measure the degrees so we know what we're talking about. So we would measure, you say, oh, that's about, what is that about? Is that about right? That's about 17 degrees. So this particular triangle measures about 17 degrees. So we'll put it right there. We'll mark it. This is 17 degrees. And we're asking on a 17 degrees ratio, on a 17 degrees triangle, right triangle, what is this ratio? What is the ratio of the opposite one, the side opposite of 17 degrees and the hypotenuse? What would this ratio be? If you're a layman, if you were just a kid learning this, just a curious child, how would you figure out that ratio? Well, I got an idea. Alright, so here's my idea. Here's my excellent ratio tool. Right here, baby. This is it. This is called a ruler. I don't know if you guys have ever seen one of these, but it measures things. So I take this guy right here, and I measure it, and I get, oh, that's approximately 21.5 centimeters. Okay? So I write 21.5 centimeters. I could measure this one over here. This one's about 22.2 centimeters. I could measure this one right here. 6.4 centimeters. That's it. If I wanted to know this ratio, this is 6.4 out of 22.2. So I simply say, okay, if I have 6, let me see if I can light it up for you. See that? So if I got 6.4 divided by 22.2 centimeters, what is the magical ratio? 28.8. So it's about 28%, 29%. That's it. That's the layman approach to ratios. Just use a ruler. Measure this, measure that, figure out what the ratio is. It's not rocket science, but it is powerful. This is so powerful because it tells you a very, very primitive way of measuring this ratio, telling you exactly what that ratio is. It's just this distance compared to that distance. That tells you the ratio. Okay, that was fun, huh? Want to try it again? Let's try it again. Let's try this one. Suppose this time I wanted to know this ratio. So it's easy. I'll just measure this. This one is 20.5. I'll go with 20.6 centimeters. This distance over here is 17.3 centimeters. So therefore the ratio is 17.3 divided by 20.6 is equal to 83.99, roughly 84%. Okay, what does that mean? That means for a triangle, this shape, let's see, what kind of triangle do we have? This is different than the other one, of course, because it measures different degrees. This one is, I believe this one is 33 degrees. 33 degrees. So this is for 33 degree angle, the ratio between, we would stand right here, we label these sides, we call this the adjacent side because it's right next to you, and the hypotenuse, and the ratio is given by 83.99%. And how do we get it? Layman approach. Nothing but common sense and a ruler, right? But you don't really think we're going to be doing this all day, right? You didn't pay 20 bucks to learn about this, right? Really, there was this is a powerful, deep way to understand what these ratios are. But there's more. People, this was good maybe in the time of the dinosaurs, but humans have an incredible spirit of improving things in life. So over the centuries and the thousands of years, we did improve this, and now we have a much more refined, much more sophisticated approach. Okay, so our ancestors had this great wisdom. they said, you know what, this approach is sort of lame. We can do much better than that. And so they said, you know what, we're going to do a more refined approach. And this has become a classic approach to doing the ratios. They said, you know what, forget about this 28% stuff business. That was just based on this stuff. Alright, let's put that aside for a second. Let's think about this. Not thinking like an insect, but thinking like a human being. I thought, we're going to invent, out of sheer audacity and out of sheer imagination, we're going to invent these special functions, little machines that do magical things with these ratios. They tell you, with these triangles, they tell you exactly what the ratios are. So what our ancestors said, they said, you know, we're going to invent a function. This one, for example, is going to be called sine of theta. It's going to behave a lot like a function. You've seen maybe other functions in your life. You've seen, for example, f of x. You've seen that function like that, right? Or g of x, or log of x. These are functions that you may be familiar with. They have an input and an output value, and the output depends very much on the input many times. That's the same thing with sine. Sine is a function that depends on the angle theta. But what it does is, if your angle theta is here, what it will do is it'll identify the sides as one of them being opposite and the hypotenuse, of course, being across from 90, and the sine of theta will be the ratio, exactly the ratio we want, opposite to hypotenuse. And it was just, we already had the concept. We wanted this ratio of opposite to hypotenuse. We just now gave it a name, and we called it a function that depends heavily on the angle theta. For example, this one would be different than the other one that we did, the one with 33 degrees. And so this function was invented just precisely to give you this ratio. Well, okay, so we gave it another name. It doesn't really help you figure it out. However, our ancestors spent years, decades, days in, days out, without food, or maybe with a little bit of food and water, just locked up trying to figure out the secrets inside sine. How they actually compute it mathematically, not with a ruler, until one day, guess what happened? Nothing happened. I'm just kidding. One day they figured it out with amazing grace and elegance. They figured out exactly how to compute sine theta, sine of any angle. And lo and behold, as soon as they did that, they opened up the doors to what we now call ratio Nirvana. They could figure out all the possible ratios. They became so good at it that nowadays you can program any old cheap calculator that you get at Walmart. You can program it and it'll tell you all the possible ratios. You remember our first estimate using our layman approach was 28%? Watch this. All I have to do is tell the calculator which angle I'm talking about. I want to tell it, hey calculator, I'm talking about the 17 degree angle triangle. Can you tell me, please, what is the ratio? And of course it should be pretty close to this ratio that we had over here. Watch this. Magical powers of the calculator. It's a dumb calculator, but really it has all the magical powers of our ancestors who really figured it out and told the calculator how to do it. Now you find a little sign button. You got to make sure you're in degrees. A lot of them have degree modes or radian modes. I've already made sure that mine's in degree modes. I go with 17 degrees and it tells me precisely, bam, right there, the ratio 29:23, or I'll round off 29:24. That is much more accurate than the original estimate that we had using our layman approach. Still, everything should come together now. All of a sudden, some very important things happen. All of a sudden, you know exactly what people mean when they type in sine of 17 degrees. It means exactly this ratio. It means that the opposite one is 29% of the hypotenuse. on a 17-degree triangle. More than that, it opens up the door to now all possible ratios, not just 30, 60, the ones that we had before. Now we know all the possible ratios. I could do 17 degrees, 18 degrees, 19 degrees, 25 degrees, 97 degrees, easy there, scratch that, I said that. I could do all the possible right triangles that I can think about, and the calculator will tell me all the possible ratios. Thanks to all this magical power that is built in there from our ancestors. And you may ask, well, yeah, how do you actually do that? Well, you gotta pay extra for that, buddy. My mom always said, if you're good at something, don't do it for free. So, yeah, you gotta pay extra to really, really know the secrets of the sign. Right now, you gotta take it's a little bit of prideless way. There's no pride. This doesn't do anything for your soul. It just helps you get the value, but that's all we have for our class for now. Unless the angle is famous, like 30 degrees. Oh, 30 degrees. All you need is heart and soul, and you're good to go. All right, let me expand on this. You remember our previous example with the layman approach for a triangle that has 33 degrees here? We had estimated about 83%. Forget about this. Now let's go for a little bit more classic approach. The classic refined approach. The classic refined approach, what our ancestors did is they invented a function. The function is called cosine. That's its full name, but it usually goes just by cos, and usually it has an input just like the regular functions do. So for this one, and it's defined to be the ratio of the adjacent side compared to the hypotenuse. So if I'm standing here in this corner, the adjacent one would be exactly this one, the adjacent and the hypotenuse. So this was tailor-made to tell me exactly this ratio. This would be the cosine ratio, cosine of 33 degrees. So you remember our previous approach, right? That's over here. Can you see it? No, you can't see it. I'll bring it over closer to the screen. This was our previous approach, okay? Let's toss that out of the way. Now we got a more classic, refined approach. So our forefathers, our ancestors, conjectured this function here, and then they spent countless hours figuring out amazingly elegant ways to compute it, to the point where they could teach this soulless object, calculator, the amazingly elegant ways. They taught the soulless calculator how to do it, and now the calculator can do it with no problems. Can you believe it? Watch this. All I do is in there, let me turn it up, I'll turn on the light for you. So now I'm going to do the cosine button, and I'm going to do cosine 33. And all I'll do is hit the, look, nothing happens to my soul when I hit this. So I don't understand, nothing, but the thing tells me exactly what I'm looking for. 83, 86. 83, 86%. That is a much more precise way of doing it, a more classic approach than, of course, the previous way, which relied on very primitive ideas. But still, man, this is life-changing. These little functions tell you all the ratios of not just 17 degrees. You don't think it just works for 17 degrees, right? Or 33. Which angles do you think this little calculator works for? Oh, all of them. Every single angle that you can think about, boom, you can put it in there, and it will tell you the exact ratio. Cosine does the ratio for the adjacent to hypotenuse, and sine will do it for the opposite to hypotenuse. Okay? But wait, there's more. So suppose this time you wanted to know the ratio of opposite to adjacent. Well, guess what? Our ancestors also left us with this excellent function called tangent. Tangent of any angle theta would be the ratio of the corresponding triangle of opposite compared to adjacent. So this is tailor-made, so that if you take the adjacent, multiply by a tangent, it gives you the opposite. Tailor-made. All you do is multiply by a tangent of 33 degrees. Tailor-made. So all I do is take my little calculator, and I go like this. Tangent. There's a tan button. Tangent 33 degrees. Bam. That means it's about 64.94, about 65%. That means if you've got this side, you multiply by 65% and it gives you exactly the opposite side. Okay? See how easy that is? Now you get all the possible ratios in the world right here. That's why this is called Ratio Nirvana Day. Remember the fundamental theorem of today, of trigonometry? Ratios are good. If you got one ratio and one side, game over. And we were okay for a while. We knew a couple ratios. We knew the 30-60, 45-45, the almost triangle. But today, oh my goodness. Today, which ratios do we know? Every single possible ratio that you can want on a real triangle. Boom. We got the three powerful functions. Let me review. Okay? Summarize. You should become comfortable with this Greek letter theta. It just means like an x variable, but traditionally people use it for angles. Theta, that's what you'd call it. So here's let me summarize the importance of today, Ratio Nirvana Day. We've got these functions. The sine of theta, this function was tailor-made to describe the ratio of opposite to hypotenuse, where across from this angle you find always the opposite, and across from 90 degrees you always find the hypotenuse. Okay, then we have cosine. Cosine was invented, it was born to give you the following ratio: adjacent over hypotenuse. This is the adjacent one. And of course tangent was born to give you the ratio of opposite to adjacent. Okay? And with these ideas, even though we still don't know how to actually compute them, well, that's complicated. We do know how to compute them, but we have absolutely no clue how the calculator is doing it. So let's just let that slide. Okay? When you get to calculus 2, you gotta pay more money for that, but we can show you the secrets of exactly how one could break this down and look at its inside its guts and stare at it inside, and oh, it's beautiful just thinking about it. Makes me want to teach that right now, but no, I digressed. Sine and cosine tangent. With this powerful calculator we can solve all the possible ratios, and the diagram to keep in mind is that tangent, sine, describes opposite to hypotenuse. That means if you take the hypotenuse, you swing it over here. Imagine algebraically swing it over here times the sine, that will give you the opposite. Meaning that if you go this way, you just have to multiply by sine theta. Whatever value that is, whatever percentage that gives you. To go this way, from the hypotenuse to the adjacent, all you do is multiply by cosine theta. Adjacent to hypotenuse, that's these sides right here. And of course, to go this way, all you do is tangent of theta. This gives you all possible ratios, just like that. With great elegance. So easy. Oh my goodness, I can't believe I get paid to do this. You want to try one? Let's pick a random one and we'll finish off with that. Okay, keep in mind what day today is. Today is Ratio Nirvana Day. We know all the ratios. Watch this. Suppose just start off with a silly little right triangle. And all you know about it is that one of the angles is 42 degrees. That's it, man. Game over. You know all the ratios. This side is opposite of 42, opposite. This is adjacent because it's, this is hypotenuse because it's across from 90. Which function tells you the ratio opposite to hypotenuse? Of course, sine. So I go on and I look at sine of 42, 66.91. Is that hard? Super easy. This one right here is given by cosine. I look at cosine. What is cosine? 74.31. 74%. 31. I want this ratio. All I do is pick up the tangent, which describes opposite to adjacent. This is opposite, this is adjacent. Next to you means adjacent. Opposite of you means opposite. And 90%. I told you, ratio Nirvana. All the ratios right here, baby. That's why they pay me. Let's take it up a notch. This is position independent stuff, man. You could be looking at the triangle upside down or right side up. Suppose you're over here standing next to the 12th degree angle. So you look across, and this one is now the opposite. This one is now the one next to you, adjacent, and this one is still the hypotenuse. But if you still wanted to know the ratio, this ratio, opposite to hypotenuse, the sine of 12 would give you that. So you would go to here. This is the steps I'm doing. Sine of 12 degrees on the calculator. That would give you sine 12. What is that? 20.79. So this is about 20%. About 21%. That means whatever the hypotenuse is, if you multiply it by 29%, that gives you this. I know these are not drawn to scale, but that's what the ratios are. I told you. I could do a cosine of 12%. I could do tangent of 12%. And what that's telling me is these ratios. This right here, adjacent to hypotenuse, which function does that? Of course, cosine. So that's about 97%. And of course, the tangent, 21%, 0.2125. I told you. It's ratio Nirvana day, baby. That's why they pay me. Oh man, now ratios are too easy. Now we know all the possible ratios for all the possible triangles. Oh, that was fun, wasn't it? Alright man, I think we should call it a night. We gotta keep this short. Peace. See you guys. Hey, you guys want to see something interesting? What's going on here? Zoom you in there. No, zoom you in. When I try to type in fundamental theorem of anything, you got fundamental theorem of calculus, algebra, arithmetic, calculus, welfare, linear. Where's the fundamental theorem of trigonometry? See, I have to do everything myself. Nobody has invented it yet. Right here, baby. Fundamental theorem of trig. It's about the ratios. Okay, now I'm out. Peace.